In section 5.6, we look at exponents and scientific notation. We have seen that exponents are used to indicate repeated multiplication. Properties of exponents allow us to perform operations with exponential expressions without having to write out long strings of factors. The first rule we're going to look at is the product rule. This just says when multiplying exponential expressions with the same base, we add the exponents. We use the sum as the exponent of the common base. So whenever you multiply, you add the exponents. When an exponential expression is raised to a power, then we multiply the exponents. This is the power rule. You'll place the product of the exponents on the base and remove the parentheses. So if you have an exponent raised to an exponent, you multiply them. The quotient rule says that when dividing exponential expressions with the same base, you subtract the exponent in the denominator from the exponent in the numerator, and you use the difference as the exponent of the common base. So all you end up doing is subtracting the bottom from the top exponent. So let's go ahead and try this with a few examples. We have 9 to the 6th equals 9 to the 12th. Well, because we are multiplying here and we have the same base, we add the exponents. So we get 9 to the 6 plus 12, but 6 plus 12 is 18. And we'll just leave this in exponential form. What about 3 to the 4th to the 5th? Well, I have an exponent raised to an exponent, which means I multiply the exponents together. So we have 3 to the 4 times 5, or this is just 3 to the 20th. We have 5 cubed raised to the 8th. Again, we have an exponent raised to an exponent, so we multiply the exponents together, and this gives me 5 to the 24th. For 5 to the 12th over 5 to the 4th, we're dividing, which means I'm subtracting. So I have 5 to the 12 minus 4, which is going to give me 5 to the 8th. For 9 to the 40 over 9 to the 5th, again, we're dividing with the common base. So we end up subtracting. We get 9 to the 40 minus 5, which gives me 9 to the 35. The next rule we're going to look at is the zero exponent rule. If b is any real number other than 0, b to the 0 is 1. So what this says is that anything raised to the 0 power will give you 1. Let's use that rule to simplify. So 7 to the 0 is 1. Pi to the 0 is 1. Negative 5 to the 0, you could probably guess, is still 1. Now for this one, we have to be a little bit careful. Only the 5 is being raised to the 0. So we could always rewrite this as negative 1 times 5 to the 0. Well, we know 5 to the 0 is just 1 from the rule, but negative 1 times 1 is negative 1. So the difference between C and D is that in C, the negative was grouped with the 5 using the parentheses, where in D, the negative was not grouped together, which means only the 5 was being raised to the 0. The next rule is the negative exponent rule. If b is any real number other than 0 and m is a natural number, b raised to the negative m is equal to 1 over b to the m. So remember that we can always write our numbers over 1. And so what the negative exponent says is that anything raised to the negative exponent just gets flipped across the fraction bar, and then it becomes positive. This works if the negative exponent is in the denominator as well. We would just flip it to the top and it becomes positive. So let's go ahead and try example number 3. We've got 8 to the negative 2. And remember, we can always write this over 1. And so that means that 8 raised to the negative 2 is going to get flipped to the denominator. And we're going to get 1 over 8 squared. And 8 squared is just 64. Be very careful with these that you don't just write down negative 64. You want to make sure you flip it and then simplify. The same idea goes for 5 raised to the negative 3. We can always write this over 1. And so the 5 raised to the negative 3 gets flipped to the bottom. And we end up with 1 over 5 cubed. And 5 cubed is 125. What about 7 raised to the negative 1? Well, remember, we can always just flip this to the bottom. And so we end up with 1 over 7 to the first. But 7 to the first is just 7. So we end up with 1 over 7. Exponents and their properties allow us to represent and compute with numbers that are large or small. There are 2 basic rules of powers of 10. A positive exponent tells you how many zeros follow the 1. So for example, 10 to the 9th is a 1 followed by 9 zeros. A negative exponent tells us how many places are to the right of the decimal point. For example, 10 to the negative 9 has 9 places to the right of the decimal point. And so this brings us to scientific notation. A positive number is written in scientific notation when it is expressed in the form a times 10 raised to the nth power, where a is a number greater than or equal to 1 and less than 10. And n is an integer. To convert scientific notation to decimal notation, if n is positive, we move the decimal point in a to the right n places. And if n is negative, we move the decimal point in a to the left, the absolute value of n places. So let's write each number in decimal notation. We have 1.375 times 10 to the 10th. So because the exponent is positive, that means we need to move to the right 10 places. So starting at our decimal, we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's where your new decimal is. In any of these blank little U's, we just go ahead and we put zeros in. So what we end up getting as an answer in decimal notation is 13,750 0, 0, 0, 0, 0, 0. Let's try the next one. We have 41.1 times 10 to the negative fourth. That means because it's negative, we want to move it to the left 4 places. Starting with our decimal, we go 1, 2, 3, 4. And remember, we just fill in our blank U's with zeros. So we end up with 0.00411. What about decimal to scientific notation? So to write the number in the form a times 10 to the nth, we'll determine a, the numerical factor, move the decimal point in the given number to obtain a number greater than or equal to 1 and less than 10. Determine n, the exponent of 10 to the n. The absolute value of n is the number of places the decimal point has moved. The exponent n is positive if the number is greater than or equal to 10 and negative if the given number is between 0 and 1. So we have 4,600,000. So to find the a, we want to put the decimal place right after the first number that is not 0. So in this case, the 4. So I'm going to put my decimal place right between the 4 and the 6. That is going to be your A. Then we know we're going to have times 10, and we need to figure out the n part. So let's go ahead and rewrite this really quick. So if I'm putting my decimal place here, how many spots do I have to move to get to the original number? 1, 2, 3, 4, 5, 6. And that's going to be a positive 6. Let's try the next one. The decimal place goes right after the first number that's not 0, which in this case is 2. So we have 2.3 times 10 raised to the, and it's going to work the same way. We need to figure out how many times we moved. So putting that between 2 and 3, we need to see how many places we moved from the original. 1, 2, 3, 4, 5 units. And we move to the left, so that makes it negative 5. Now, how do we do computations with scientific notation? We use the product rule for exponents to multiply numbers in scientific notation. As a reminder, that just says that if we multiply with the same base, we add the exponents. So you'll add the exponents on 10, and you'll multiply the other parts of the number separately. So let's try this with example number 6. 3.4 times 10 to the 9th times 2 times 10 to the negative 5. We want to write the product in decimal notation. So we have 3.4 times 10 to the 9th, and we have 2 times 10 to the negative 5. We're going to multiply the A pieces together, so 3.4 and 2, and we're going to multiply the 10 pieces together. So we have 3.4 times 2, and this is still times 10, but now we want to add the exponents together. So 9 plus negative 5. 3.4 times 2 is 6.8 times 10 to the positive 4. And so we need to convert this to decimal. And that means we need to move this 4 units to the right. So we end up getting 68,000 as an answer. When we divide, we're going to use the quotient rule, which just says that we subtract the bottom exponent from the top exponent, and we'll divide the A pieces on their own. So let's try this with example number 7. 8.4 times 10 to the negative 7 all over 4 times 10 to the negative 4. So again, we want to take the numbers out front and we're going to divide those on their own. And then we're going to use the quotient rule with the 10 part. So we have 8.4 over 4. We still have times 10. And then the exponents, we use the subtraction rule. So this is negative 7 minus negative 4. Well, 8.4 divided by 4 is 2.1 times 10 raised to the negative 7 minus negative 4 with the double negative. It's going to give me a plus, and so we end up with negative 3. So we got to convert this to decimal notation. And because it's negative, that means we're moving to the left 3 units. And so we end up getting 0.0021 as our answer. And for the last one, we have 0.00064 times a really long number, 940000000. We want to express the product in scientific notation and decimal notation. The first thing we want to do is convert these to scientific notation because they're just super long. So let's look at 0.00064. And we want to write this in scientific. So remember that the decimal point goes right in between the first number that's not 0 and the rest of it. So we have 6.4 times 10, and we need to see how far we are moving it. So we have 1, 2, 3, 4 units, and since it's to the left, it's going to be negative 4. We want to do the same thing for the other number. So remember, the decimal place goes right after the first number that's not 0. So in this case, it's 9. So we have 9.4 times 10 raised to, and we need to figure out how many times we're moving it. Looks like 9 units. And it's going to be positive because we moved to the right. So now what we're doing is we're multiplying two scientific notation numbers. We've got 6.4 times 10 to the negative 4, and we have 9.4 times 10 to the 9th. So just like in the previous problem, we're going to multiply the 6.4 and the 9.4 together, and we're going to use the addition with the tens on the exponents. So we have 6.4 times 9.4, and then we need to add the exponents. We have negative 4 plus 9. So 6.4 times 9.4 is 60.16 times 10 raised to the negative 4 plus 9, which is 5. Now, is this scientific notation? It isn't, because our A is 60, which is definitely bigger than 10. There was a stipulation that A was greater than or equal to 1, but less than 10. So what we would end up having to do was, if we move the decimal place 1 point to the left, we would get 6.016 times 10 times 10 to the 5th. So let's go ahead and rewrite it. 6.016 times 10 is how I would move the decimal to the left 1 unit so that my A is in the correct format. We still have our 10 to the 5th, but remember, these all have an exponent of 1 if it's not explicitly written. So we can rewrite this as 6.016 times 10 to the 6 because we add the exponents together. And so that is scientific notation. We also want to write this in decimal notation. So we would want to move our decimal place 6 units to the right. So we have 1, 2, 3, 4, 5, 6. And so we also get 6, 0, 1, 6, and 3 zeros afterwards.